Hello, hello. Jimmy, that background still creeps me out. Can y'all hear me? Okay, cool. Thanks. Hi. Jimmy just looks like he can't. Hello, hello. Hello. Welcome, everyone. How's everyone's Saturday going?
Going well. How about you?
Doing pretty good. I was in Hollywood earlier, so living that LA life.
What were you doing in Hollywood?
My friend was house sitting in the Hollywood Hills, so we were like living that rich lifestyle, you know? um, so yeah, went on like a hike and saw the Hollywood sign. So very cliche of me. But yeah. How about anyone else do anything fun this morning? No.
I went on a walk through like South Berkeley, and my friend and I talked about all these new buildings that they're making and like how ugly they are. Like the one on Telegraph and Regent, I think, like around that area.
Is that the new like dorm one or is that a different one? Like
It's not a dorm. It's this big green building. It's like the McMansion version. It's like a McMansion in Berkeley, but it's an apartment building. It's really bad. Not a good scene.
awesome. The pictures I've seen of that like new building that looks like I don't know how you guys all know what I'm talking about with that like gross building. Bad
Oh,
vibes.
the big brutalist building on Channing or Durant.
Sure.
I
I've never
think
seen it in person.
I think it's on Haste and Telegraph, right? It's like across kitty corner from
No.
Amoeba, right? Or I don't know. I think so.
Hey guys.
Hello. We're just talking about ugly buildings in Berkeley. So
Oh, you mean on campus or?
no, like off of campus, like Telegraph.
Oh God, you mean that like crazy stone building?
Yeah.
Oh, God. Is anyone living there? Okay, good.
It's like kind of grown on me though. Like I like not that I like it, but like I when I first saw it, I was like,
Offended.
yeah, no, like actually, but it's like not. It's like okay, I guess. I don't know.
Do you know anyone that lives there?
I don't.
I do know someone that lives there in that big Atlantis building. Yeah. Apparently like it's a nice place to live. The neighbors are nice, the landlords are very responsive, but it's just disgusting and just an offense. My personal opinion, but yeah, apparently it's, a place to live.
Yeah. I'm
Awesome.
gonna put out a reminder, Jenna.
Awesome. Thank you. Eddie. Hello, Eddie.
Hey, Jenna and Ophir, can you tell me how many hours you guys have spent prepping so far? You can Discord me, or yeah, just let me know so I can track it.
Oh no. Okay. I will do that later. Thank you. Okay. Should I wait or just get started? Just we won't get into like the coding for a little bit, so it's like okay if they miss miss this first part. All right, let me get this presentation up. Okay, so we wanted to start with just like a quick intro to AI and like make sure we all have the same definition and understand why it's important, as well as if you want, I will be sending this in the Discord that if you have any students who you think would find this interesting and be a good platform for discussion, you can also totally take it and adapt it in any way. But we thought it might be interesting and we wanted to start each class with like a kind of general discussion about our own ideas and debate some popularized topics about artificial intelligence. So let's talk about AI. So what is AI? So within this workshop, and the most common definition I have heard is that AI is a science of designing machines that think and act rationally. I've heard the phrase that AI is the science of making machines that think and act like humans and think and act rationally, which I find kind of contradicting because humans don't always act rationally. So like I think that the main focus of AI is rationality and less so to fully mirror the human experience, which could cause some errors down the line with some of the topics we'll talk about. But in general, that's what AI is. So why should we care about AI? So there's two different areas that I think we should care about. So I really care about cognitive science and neuroscience. And so AI allows us to study how the mind works and kind of make hypotheses about how we can study the mind and incorporate a very wide range of different ideas like neuroscience, psychology, linguistics, and more. So that's really interesting for me. But for coders, it's also really interesting because it allows y'all to find solutions to problems that you may not be able to find on your own. And it allows you to analyze data in a new and unique way. So a great example of this, if you were to make a spam filter for email on your own, what would you do? And this is open to anyone can unmute and say what you would do. You can think about it too. Anyone, any ideas? Is that an idea, Jimmy? Is that a hand? Do you want to say an idea, Jimmy? I think you're muted in case you don't know.
Oh yeah.
The
No,
chat.
so I would definitely set a filter for newsletter of some sort.
Okay. Anyone else have any other ideas of what you would do? If not, I'll move on. I don't have access to the chat, so if you put anything, just let me know. Cool. Okay, so go for it, Cameron.
Oh, okay. I know that one thing that I think Google, like Gmail does is like they have like a big data set of all the emails ever. And then like as time goes on, like with like machine learning algorithms, they can perfect like what emails are spam and which ones aren't.
Exactly. So like, for instance, if I looked at my email right now, let's say I see all of my spam has the term like free raffle or something. I don't know what spam does. I don't look at it anymore. But let's say I notice all of them have free raffle. So then I would filter and tell my computer anytime I saw a free raffle to put it in the spam filter. But then the spammers would catch on and realize that I was doing that. And then they would just change their phrasing. And then all of a sudden it wouldn't get filtered out anymore. So yeah, like you said that Google is always, or like anywhere, is always adding to their data set and using machine learning. It can learn it as it goes. and doesn't require us to constantly be reworking and changing the phrasing. It will just be finding it on its own. So that's why AI is really helpful in helping us find new solutions and really help us work smarter and not harder, because then we don't have to constantly be like thinking about what else people can do. Beautiful. So a really quick history of AI that I think is important is, so during the Cold War, researchers realized that if they connected their projects to war, they would get funded. So Norbert Wiener proposed the idea of cybernetics, and cybernetics was the theory that would cover the entire field of control and communication in machines, as well as living organisms, and could be used to model everything. Like, he was swearing that it could model everything from war to just literally like how walking around the block works. Like, he was like, this will connect to everything. And it was made to simplify assumptions to build predictors. But over time, it disappeared in the 1970s, kind of because they couldn't disassociate the idea with Wiener. And Wiener was kind of crazy at the time because he was not a fan of war, and he spoke out about that. And the Soviet Union was like, yo, I really respect your ideas. So everyone totally disassociated with cybernetics, but it lives on in popular culture because, like, we all say cyborg, and stuff like that. So, but AI is an intellectual enterprise of post-World War II cybernetic era, and they basically differ based on early AI researchers were mostly just interested in understanding human intelligence as they were producing an intelligent machine instead of trying to create it to predict everything and be applicable to everything. So this I'm not going to go really deep into because I found it online and I don't feel too confident about all aspects of it, but it roughly just shows the timeline of artificial intelligence and how it started around the golden age of science fiction, and it's gone all the way up until now. And we can kind of see the spike and how it's grown and changed over time. But it's kind of interesting, like, for instance, like Alan Turing, who we'll talk about a little bit later, that was in like the 1950s, and the first AI program was invented in the 1955. So obviously we've come a long way since then. So AI is all around us, and it's not just like robots trying to take over the world like a lot of people are thinking it is, but it's really just trying to find ways to help support society to help us work smarter and not harder. So some that I think are the most well-known are Uber and Lyft. For all their rates and routes use AI. Email spam filters AI, plagiarism checker, even depositing checks, and obviously Siri and Google Home. So AI and deep learning is rooted in neuroscience. So kind of like the ideas of cybernetics, they use the human body and our brain to start how machine learning works. So I thought it would be helpful for us to just really quickly discuss how our brain works. So I think this is a really cute and easy way to understand how we see something, we process it and understand it with our nose, our eyes, all of our senses. We all know this. Then it goes into the brain and it gets perceived, and then we understand what to do. So like when you smell something bad or something, you would then plug your nose or whatever you need to do. You see that there's a hot pan and your hands on it and you feel the heat, to remove it. Or like this pug smells the pizza and starts drooling. But if we look even closer into our brains, we have neurons. So I think everyone knows what a neuron is, but this is the rough outline. And basically there's a bunch of neurons that are talking to each other, and they have to hit a threshold to trigger onto the next. So basically it meets at these dendrites, and then it would go swoop right through this whole neuron if the energy was met. And we can see how this is a great model for neural networks, because we have a bunch of inputs and we have to find the perfect weight to then make an output. So kind of similar to a neuron, it has to get that perfect amount of energy, the weight, and if it does, then it will go through and process to the next one. So neural networks are systems designed to roughly resemble our brains, animal brains, and their ability to learn tasks through examples rather than being programmed with rules, because like we said, you don't always know exactly what you are processing. You can't be like, do this, then that, because you want it to learn. And it does pattern recognition equated with learning. Functions are based on the neural structures. So we have our neurons, which equal nodes, and we have our dendrites, which equals the input and propagation. Okay, that's just a really basic thing, but I think it makes sense that like you just need a certain amount to trigger the next one. So some of these are three topics that we'll get a little bit more into later, but I think are interesting and would love just a little discussion at the beginning just to get us thinking about it. But I think three of the important ideas is ethics, intelligence, and bias. Ethics and bias kind of go hand in hand, but I think they're different, and I will tell you why. So for ethics, there is like two kind of main ideas I want to talk about. So in one of my classes, I had the head of security for Obama come and talk to us and tell us this like horrible story and hypothetical of if you were in war and you sent a drone to just go and scope out this city, they would see this little girl and realize that they were a spy and just kill the girl. But if it was an American soldier, because they're so ethical and awesome, they would notice that this is just a little girl and it's wrong to kill him, you know? So he brought up the idea of AI in war and the ethics and teaching them what's right and wrong. And with warfare, it's kind of scary because we all have this technology, but who's to say if they're actually being ethical with their technology? Like, because right now you could easily have drones just go and kill a bunch of people, but it's not ethical. So it's where does that line get drawn? Which is a sticky one and was very interesting hearing him talk about it. But then the other side is this example of the paperclip maximizer. I'm not sure if anyone has ever heard of it, but if you program an AI to just get as many possible paperclips, all you want to do is maximize the amount of paperclips. As you improve the intelligence, it could possibly get so massive that it would eliminate humanity and all humans would become paperclips in its mind. I know it's pretty absurd, but it's the idea of like how it could get out of hand if you don't have ethics in place of the AI could convince itself that humans could become paperclips at some point. So it's pretty wild and out there, but those are two sides that like ethics need to come into play or else real consequences could happen. Obviously, a machine's not gonna be like humans become paperclips and kill all humans to make us paperclips, but it's still the idea of the extremists' perspectives. So then there's intelligence, and I think this is a really interesting topic because how do you define intelligence? Which is a very generalized idea. And AI is trying to develop intelligent machines that allows us to explore the principles that makes the mind work and try to build minds in a good way to test theories about their properties. But it's like, how do you define intelligence and how do you test intelligence? This is still like a really big topic outside of AI and just in like cognitive science and like psychology in general. But with AI specifically, how do you test your machine's intelligence? Are they actually intelligent and learning, or are they just following an algorithm? Is following an algorithm intelligence or not, etc.? So next time we will go into this a little bit more. But Alan Turing, who's this guy right here, was a mathematician who cracked the Enigma code. And if you've ever seen Imitation Game, it's all about him. But he created the test, the Turing test to help computer scientists understand the limits of mechanical computation and explore how to judge success in making intelligent machines. He kind of coined the idea of there's weak AI and strong AI. And weak AI is like AI who's just following an algorithm, where strong AI is people who are robots, AIs who are actually thinking on their own. And Turing kind of believed that it's impossible for there to ever be an actual strong AI. And then we can go through and kind of contemplate next time. We'll go through a bit of chatbots and see if we can determine what makes them weak or strong AI. And the last one I want to talk about is bias, because I think this is a really big issue currently. Of everything you program, your bias gets into your program. So if you don't recognize your bias, you could possibly be making a biased AI. So one of the scariest examples, at least to me, is Teslas and their self-driving cars that within their program, it's actually easier for them to recognize lighter skin than darker skin. And they didn't go the extra mile to make that not happen. So like some people may argue that it's light and sensors, but I think if that was something important to you, you would really go that extra mile and that your bias is really entering your AI. Similarly, if you voted in California this year, I believe it was like Prop 25, maybe 22, which was contemplating if we should change the cash bail system to an algorithm to determine the threat level of these individuals. And the main critique of that idea was that this algorithm is actually really biased, and it will take this data of like how many times you've gone to jail to help determine your risk. But then it's like, it's statistically proven that if you are darker skin, you will get to jail more likely than someone with lighter skin, and thus like not recognizing the bias, which could impact so many people's lives. So I think in general, it's just nice. It's important to note how you as a programmer are not separate from your program, and we need to be aware of how our bias can impact our programs when it's important. Like, for instance, Tesla could accidentally kill someone by hitting them by not having this recognition. So that was kind of like a lot of really quickly because I talked fast. But does anyone have any questions? We just wanted to give a really general basis before going in so you could talk about AI a little bit more freely in a theoretical basis. So does anyone have any questions about that or about anything? Do happiness and sadness stop the transmission of neurons? That's a good question. No, I would say no. Happiness and sadness impacts a little bit different than the transmission of neurons, I think. Is Lena still on here? I'm like, you can confirm it.
Still here. Yeah, it shouldn't, it wouldn't. It would require something chemical or
Yeah.
physical, I think, to stop the transmission of neurons.
Yeah. Okay. I was like, I'm pretty sure, but I'm like, I need some confirmation because I never believe myself. So thank you.
It could like dampen the effects of the neurons, or it could, I think if you're like depressed, for example, it might diminish the impact of the neuron, but it wouldn't block the transmission of it.
Thank you. Cool. Awesome. So then with that, I will pass it on over and we'll get into some coding.
All right. So I trust everybody is familiar with REPL. Is anybody not familiar with it? Okay. So I'm going to ask that before I even start the presentation, just go ahead, open a regular REPL with Python, have it open. We'll be using it pretty shortly. So go ahead and open that up. Okay. All right. So just as a background really quickly, if you're all familiar with AI, you know that there is a lot of math that goes into it. I will not be going over all of the math. That this workshop is not meant for me to explain to you the linear algebra behind everything. Frankly, I don't know the linear algebra behind everything. I mainly know how to use it, so we're on good ground here. If you are interested though, I did provide some links. You can go more and research more into it if you want. I'll be touching pretty briefly on some linear algebra topics, but nothing too in depth. Like I could present this math to a 16-year-old and I'm pretty sure they would understand it. So not much math required today. All right. So models we will be learning linear regression and potentially polynomial regression. This depends on time and how much time it takes for you guys to do the activities. And we will also be going over classification. Now, you're probably thinking to yourself, there's nothing here about pandas. If you know what pandas is, it's a way for us to analyze spreadsheets using Python. We will be going over them in later sessions, but because pandas is a pretty heavy library, I thought it would be better to go over the models first with like basic data, and then we'll go over how to analyze some larger data. So without further ado, let's get started. So this is a general guideline that I like to think about when I'm designing any sort of AI. It applies to everything, all AIs. So the first thing you have to do is define your data table, or like your data in general, especially data tables though later on, which you will see in classification. It really does matter how you define it. Collect your data. Obviously, we won't be doing too much collection of data here. That's more for researchers, right? We're just writing the code. Yeah, so then we'll be choosing a model. We'll be covering a big two today, so regression in general, as well as classification. And then you would do the actual coding, which would be the machine learning, the modeling, the fitting. This part, at least at this level, is actually pretty short. The longer part is the first three, honestly. And then prediction. So prediction is obvious. We want to be able to use AI to make decisions, make predictions. So that's kind of like the ultimate goal. We know we did it correctly if this works. All right, let's jump into regression first. So most of you guys are probably familiar with linear regression from either your stats class, or I think it was covered in Algebra 1. Linear regression, right? We have the regular y equals mx plus v. You can even put data tables on Desmos if you're familiar with it, and it will give you the equation. Now, there are a couple of values here. I don't know if you can see them because they're pretty small. There's like r squared and r. Those are going to actually be relevant to us today. So if you don't know what this is, keep this in mind. I will be going over it some more. Now, you're probably also asking yourself, well, geez, Ophir, linear regression is so easy. I could write a data table in Desmos and it will kind of do it for me. Why do I need to write code for this, right? Like, I thought so too. We will be going over it in a minute. It's actually a really cool reason that does rely on linear algebra. So be prepared for that. So some obvious observations, and I'm pointing these out because these do tend to confuse people actually. So it's very clear when you graph something, when something is linear versus when it's not linear, right? So this is something that actually trips up a lot of people who are just starting to learn AI, because the data set, if you're just looking at it, is not always clear-cut, linear, not linear, classification, or other models, because there are so many models that you can use. It's very, very difficult to decide which model is going to be the best one. So when we're talking about linear regression, I really do want you to keep in mind if it is actually linear, and if you are having any difficulty with it, I even sometimes just go on Desmos, I graph it so I can visualize it, kind of see if I'm even on the right track. So if you have any difficulties at all, which I will be providing you with some data tables, feel free to open up a Desmos if you want to visualize it. Okay, so misconception about linear regression. This is the big one, right? Like, Ophir, why are we not using Desmos? This is the reason. There does not need to only be one value for your input. We are going to be using a linear algebra concept called multiple linear regression. If you took linear algebra, you may be familiar with it, you may not. You don't actually need to understand the model in order to understand what it does. So there is this little box at the bottom that kind of explains what this model is like, why it does what it does. But essentially, we will be using multiple independent / explanatory variables to determine our data. And again, this is the big reason why we use code for this rather than Desmos, because Desmos, as far as I know, is not capable of doing this. It may be. I'm not a Desmos. There are some people who call themselves Desmos coders. I'm not one of those people. So if you are, and this is possible, please correct me. But yeah. All right. So structuring input versus output, this is going to be exceptionally important to everything that we do. Okay, when we're not using CSVs, so AKA when we're not using pandas, we will be structuring the input and output of the program using nested lists. So this is more common in Python than in other languages. So yeah, but nested lists are going to be exceptionally important, especially when you're doing input data and have multiple explanatory variables. So since we're training a model with both input and output, there are some models which we're not training with an output, but we will not be going into them today. So you're going to have two lists. So input data, you will notice, has two nested lists, and output is just one regular list. What this is essentially saying is that with the independent variable values, 1, and 9, we have the value 10 associated. So it goes like this in order. So with 1 and 9, the value 0 is associated. With 1 and 10, the value 10 is associated. These numbers right now don't mean anything. They may mean something in the upcoming exercise. So do keep that in mind. Before I move on, do we have any questions about the material that we just covered so far? All right, awesome. So moving on. Okay, so practice 1A, 1B. By 1A, 1B, I mean steps 1 and 2. I will be giving you a link to a spreadsheet, and I will want you to make a copy of it and write on it on your own. This is just really helpful when you visualize stuff. So we're trying to predict the waiting time for Hyperspace Mountain Ride. If you've ever been to Disneyland, it's one of the most popular rides, and it's an insanely long line whenever you go. It's like 90 minutes. So we're going to try to predict the time it will take based on many different features, such as day of the week, holiday, and time of day. The link I will provide you will have a legend. So what the legend will mean is we're going to be converting stuff like holiday or not to numbers. So if you're at all familiar with binary, 0 is going to be false, 1 is going to be true, etc. So I will give you the link to this spreadsheet. And I do encourage you not to use random numbers, which you can, honestly. I'm not going to tell you what to do and what not to do, but it will be better if you don't use random numbers. If you want to like research, go for it. There are plenty of resources, especially for this online, because people get really annoyed when they have to wait in a 90-minute line. So yeah, I sent a link to you guys in the chat. So feel free to fill up a spreadsheet however you want. You're free to use online resources. This should take you about like 5 to 10 minutes. You don't even have to fill all the rows. I just put some rows for you guys to use. You can use less, you can use more, but do keep in mind your model will be more accurate if you use more. So that's another big one. All right, so 5 to 10 minutes. If you finish earlier, just let me know in the chat. And if everybody finishes early, we can just move on.
How should we put in time of day? Should we like military time or?
So time of day just go with like 0 is 12 a.m. and then 24 is 12 p.m. So the 0 to 24 scale.
Okay, great, thank you.
Mm-hmm. And by the way, as long as you keep it consistent though, it shouldn't actually matter too much. So yeah, that's just what I'm going to be using.
Okay, sounds great, thank you.
And again, once you're done, feel free to either put yes in participants, like, the yes button participants, or say yes in the chat. Either one of these will work, just so I know how much more time people need. Okay, very cool. Seems like almost everybody's done. Okay, I'm just gonna. It seems like almost everybody's done, if I'm including myself as well. Yeah, okay. So I think we can get started then. If you just want to add or subtract a couple if you could not fill up the space, no issue there either. So feel free to do that. There is no specific amount of data that you need. Okay. So now we're finally going to be doing the model and fit. Actually, wait, is that model and fit yet? Or I think we have to, no, okay. Okay, so everybody open up your REPL if you haven't already. Use the following import statement. So from sklearn, import linear model. So sklearn is going to be the library that has all of our models in it. It will have all of the models until a pretty high level model. So no worries about that. Pretty cool library if you want to look into it. Okay, so put your input and output data in the structure that we discussed earlier. So this is kind of like, it's a bit time consuming when you do this, but you have to put in your input data and your output data in the proper structure. So again, input goes in nested lists, output does not go in nested lists, but they do have to coordinate. So make sure that you do that. And again, either say yes in the chat when you're done or say yes in participants. Either one of these work.
Hey, Ophir, can you show like the slide from earlier that like showed the example of this?
Yeah, let me do that. Right over here. So if you have, in our example, let me take a look at the spreadsheet really quickly. I believe we have three. So we have three stuff that we want to put in our input. So the time of day, day of the week, holiday or not, and then time of day. Do it in that order. because when I give you data later on to predict with, you don't want to get confused about what I'm talking about. I'll be using this order. And it does affect the model if you switch up the order for obvious reasons. So yeah.
So the input data, like they're going to be nested lists, and they're going to be like holiday or not and day of the week.
Yeah, so if I was doing a nested list for this one, just these are not accurate numbers. So just for example, so I'm just saying, let's say input data, and I'm making this equal. And let's say we are on Sunday, so 0. We are on 10 a.m. in the morning, or sorry, it is a holiday. Let's say it's a holiday, and then it's 10 a.m. in the morning. This is how my nested list for that row in the table would look like. So like each nested list is a row in the table, but you don't include the output. The output has to be in a completely separate list.
Okay, great. I'll do that. Thank you.
Mhm. And again, just so I know when everybody's done, don't forget to say either yes in participants or yes in the chat when you think you got it. All right, so it seems like almost everybody's done. All right, so I think I can show you how we can do the model now. Okay, so actually, the model is the easiest, simplest part in this exercise, in my opinion, at least. It's only 2 lines of code. So you do the following: model equals linear model dot linear regression. So this will just return an object that is going to be our model, right? And we're going to store it in a variable. Make sure that you imported exactly as I showed on the screen earlier. Otherwise, this will not work. Because if you did this, just as an example, instead of linear model with an underscore, you just called it linear, then what you want, then this will not work. So you have to make sure that you imported it correctly. And okay, and then model.fit, this does not return anything, so you're completely good. No need to store anything. And you want to feed it the input data list and then the output data list. So in that order, like X, Y coordinates. So yeah. And by the way, if you have any bugs and you want my help in debugging, I have no issue if you send me your share link in the chat and I can help you out. But other than that, at this point, this should run. You would not be seeing anything quite yet because we didn't actually make the prediction, but this should run. And again, let me know in the chat when you're done. Also, by the way, the convenient thing about this library is that for all models, the word fit would work when you fit the data. So for each new model, you don't have to learn completely new syntax. So it's going to be pretty nice.
So the model in the first line does not have to be the same variable as model in the second line? Is that what you're saying?
Which model are you referring to? Like this model? Oh, no, sorry. I just noticed that. This is AutoCap. This should be lowercase m. Like both of them have to be the same name. Sorry,
Oh.
I can change that really quickly. Yeah, let's change that. Here we go. Fixed. Good point, yeah. And the arrow, by the way, is just an annotation. It's not an actual code. Like after whatever's after the arrow. Yeah. And again, don't forget to let me know when you're done, just so I can know when to move on to prediction. All right. Looks like everybody's got it. Okay, let's move on then. So prediction is also really, really short. Okay, actually, let me give you something different to predict because I just realized in this one there's no holiday or not. So let me fix that really quickly. Let's make it not a holiday because most days are not holidays. Okay. Okay, so use the model object that you have now. So predict waiting time for Sunday at 12 p.m. on a non-holiday. So this is the prediction format. All you have to do is write model predict. Now this will return a number, so you probably want to print this out. So you probably want a print statement around this entire thing. And now pay really close attention because even I tripped up on this when I was learning this. This is still a nested list. So this is still a nested list. Even though you're only putting in one input, it has to be in nested list format. Yeah. So go ahead and do that. You should be getting a pretty decent prediction for the, hopefully, otherwise we may have picked the wrong model for your data set, but which we will be able to tell in like a second. Remember I mentioned the R² variable, don't forget that. Yeah, so go ahead, give this prediction a run. And again, don't forget to let me know in the chat when you got it. All right, looks like everybody got it. Okay, just out of curiosity, what are your models saying? Feel free to either turn on your microphone and write in the chat. I'm curious from your data set if I decided to go to Disney tomorrow. Nice, okay. Cool, oh my, Jenna is not having a good prediction today. That's like 88 minute, oh no. Cameron, I might just go with your model because I want, you know, best case scenario. Cool, all right. Okay, let's see how accurate your datas are. So let's see whose data I should look at more. Okay, so remember that we talked about R², right? So this is a function that we can use to get the accuracy score. Essentially, this is the R² of your data. If you're all familiar with statistics, the closer it is to the absolute value of 1, the more linear it is. So that means your model is more accurate. So go ahead and give this a try. So obviously this returns the score, so you'll have to print it out in order to see it. And feel free to send it to me in the chat. I am very curious on whose model I should actually follow. So, and by the way, input data, output data, the exact same lists that you used earlier should work. Oh no, Cameron. Oh no. Those are such, oh no. So if I was my stats professor, those numbers would not make me happy. So sad. Oh wow, Nick's is really accurate. Okay, what was your score? So 25 minutes wait time? Okay, wow. All right, Oliver, really nice score too. Wow, okay, so now I know whose model to follow. Oh no, but Oliver gives me 67 minutes. I'm not sure I'm happy about that. Okay, so really good job, guys. So this basically covered linear regression. There isn't really too much to it when you really break it down to like functions and how we use it. So what's the I think we do have some time to go over polynomial regression. We would be speeding through this a lot more because it uses basically the exact same structure as this one. Doesn't take too much more info to think about this. Okay. Polynomial regression, same diagram as before, though this time we're drawing a way more accurate model, right? So this one, there are a couple of reasons it's harder to use. Oh wait, do you guys want a 5-minute break before we do this? Or do you just want to go through it? You can thumbs up or thumbs down for yes, 5 minutes break, thumbs down for no 5 minutes break. Okay, no 5 minutes break. Okay, so let's just continue then. Okay, so really quickly, polynomial regression. Obviously, this model is a lot easier. Now, the biggest reason why I personally, when I write AI, I don't usually like polynomial regression unless I'm doing something really scientific. I'm going to show you this in a second, but I really want to explain the reason really briefly. You're going to have to tell it the degree of the polynomial. So in this exercise, I will be providing you with the data just because I know that it's going to be with a degree of 2. This is the biggest issue. So unless you graph it, it's going to be really difficult to tell what degree you have just from looking at the data. So make sure you really quickly import these on top of the other imports that you have. You also may want to comment out our previous linear regression code. And then for classification, you will want like a whole new REPL. I don't recommend writing on the same REPL after this. Yeah, make sure you import these really quickly. Honestly, wait, maybe I could just send these to you in the chat because that's a lot to write. Yes, okay, let's do that. Okay, here we go. So these are all the imports in the chat. Hopefully that should cut the amount of time that we spend on just some syntax. All right, so honestly, maybe I should send this to you in the chat too because I'm a nice person. Okay. Sometimes my students, when I actually teach, they try to bribe me to give them the code in the chat, and I'm like, no. But this time, we're gonna give this in the chat. Okay, so notice that even though, you can actually see this, even though my input list is single variable, I'm not doing multiple independent variables in this one, I still put it in nested list. This is just because the way that the library reads this code. So you're gonna have to do that. Almost no matter what, until you use CSVs, and Pandas does this for you. So you won't have to worry about that. Yeah, so all of these are in the chat, so I'm just gonna move on to the model. Okay, so this one you will have to write. Unlike linear regression, model building for this one is pretty complex. If you wanna go into Ridge some more, I will not go into it too much in depth. I did provide a link, so let me know if you want it. Okay, polynomial features indicates the degree of the polynomial that we were expecting. Now, from the data that I provided you, it's pretty clear which degree we were expecting. It's pretty clearly a sort of parabola. And the ridge. Okay, so ridge is pretty complex. It was built essentially to optimize least square regression. This is deep linear algebra topics. I can send you guys the link in the chat if you want to read on it more on your own, but this is like the math level I said we won't be going into. Yeah, I can send the link in the chat. Here we go. The documentation for sklearn is very useful, but they kind of structure it weird that just for polynomial regression, you have to look in many different places. So let me know if you want to find something in the documentation. By now, I pretty much know my way around it, but it's not easy. So yeah, go ahead and write this line of code then in the code. Oh, and by the way, don't forget to let me know in the chat with a yes when you're done with this model stuff. Okay, great. Everybody done. All right, so fit and prediction. As usual, we're using the exact same formatting. This is the nice part. You do model fit, you do model predict. Make sure that in your predict, you are having a nested list, even though you only need to put in one value. But go ahead, try this out. There is no specific value that I want you to provide a prediction for. So just try it out on your own. Yeah. Again, the nested list part is stuff that really trips people up, and it will continue to trip people up in pandas because, yeah. And again, just let me know with a yes in the chat when you're done with that. And again, in my opinion, polynomial regression is not very convenient in Python, just because you have to provide them the degree. There are better softwares that do this, but sometimes you may find yourself in need of it. So it's better that you know it than you don't. Okay, moving on. Okay, now time for my personal favorite model, classification. This one is, I think, as useful as you can get at this level, especially. So it's going to be pretty fun. Be prepared. Before we start, actually, because this is going to be the last big section for the class, anybody want to take a quick break before we move on, or do you guys just want to dive into it? I'm seeing some shaking heads for no. Okay, let's get started then. Okay. All right. So classification is an AI technique in which a model learns to assign a provided class to values in the data. So for example, this is going to be a very simple example. Obviously, the examples are going to get a lot more complicated, but simple example. We can use this linear classifier that aims to tell us whether a flower is a rose or a daisy. So in this model, we're doing white, white, red, pink, red, white, 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 right? And it's like daisy, daisy, rose, 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 daisy, daisy. So notice here that this model is not actually going to be represented in the data in a second because there is going to be a catch. So it might look like this. I really want you to notice the line that is drawn here. We will be going more into depth about why the line is drawn the way it is. So pretty simple. If I wanted to add just a random red flower, though, you'll probably be telling me it will go on the bottom side of the line, because up here it's all white, down here it's like red, right? Okay, so Daisy versus Rose. So far, what it looks like the program did is place the daisy and roses on different sides of the line, right? And again, random flower that is red, you'll probably be telling me it goes on the bottom side, like the computer would probably tell me, but it's not necessarily a rose. What if I had like a red daisy? I don't know if those exist, but if I had one, right, it would not be classified correctly. Okay, so this is exactly why the model is problematic. It has very few data points and it's only using 2 things to base its decisions on. This is typically why we don't just use a basic linear classifier, because it really doesn't do us any good. So let's try using 2 things to base our decisions on. What if we had a white rose, for example? Our model will think it's a daisy right now, because if we're just classifying based on color, it's very clearly a daisy, right? So anybody has any ideas? I'm genuinely curious if you guys have any ideas on what to classify this in addition, right, to base our points on. I had one idea, but I've had students that had different ideas that could work as well. So I'm genuinely curious. Write it in the chat. Feel free to do it either private message. Flower diameter is a pretty good idea. Yeah. Okay. Anybody else has any ideas? I'll tell you what I used in a second. Petal shape, yeah, edge shape. So when we say shape though, right? Here's the difficult part. Imagine you're a researcher in the field, right? If you're trying to describe to me a shape, you'll have to have like keywords to identify it, yes, no, right? And it's like, shape is a bit more than a yes, no, if you get what I mean. So that's why I would be pretty cautious with using shapes. Anything that is measurable or completely binary, yeah, you probably is a good idea. So here's what I came up with, though flower diameter can work really well. Thorns. Roses have thorns, right? Daisies, I have never seen a daisy with a thorn. If you have, please let me know. We will need to update this model. But thorns are yes or no, pretty simple. And no is 0, yes is 1. And here I would be able to classify my white rose because now I have an extra data point that I can use. Okay. All right, so SVM is the model that we're actually using, because I call this classification so far, but you're probably wondering what the heck is classification, right? Linear regression is pretty clearly using a linear regression model, right? But classification has actually multiple models, but we will be using SVM. Okay, so the position of the data in 2D space is going to be based on the data's features. Now, this is a bit of a rough one to wrap your head around. So I really want you to think back to this example. The feature that we were identifying here, right, I would say, let's say thorns in color versus color, right? The position on this 2D space is based on the features that we identified. And that's going to be extremely important for SVM. We're not going to dive into the math behind this, but this is kind of like extremely linear algebra based, super important. Okay, so for example, if each shape was a mouse, then it would be plotted against its height and weight. Then the color and output would be whether the mouse is a beast or not. But how do we know what the line of best fit is? It's not what you think, let me tell you. So support vector machine, SVM, popular class method. Let's take a look at this data. And we aim to predict if the data is red or blue. Now you're saying this is very clear. You're going to tell me the right is red, the left is blue. Pretty clear. There are also circles, right? But what if I ask you to draw the line of best fit? So Jenna, the poll goes right now. I want to see what you think. Which one of these is more correct? A or B? Let's see what everybody thinks. A or B? Where do you think the line of best fit goes?
I'm not sure if I'm waiting on anyone else's vote, so I'll give you like 10 more seconds and then I'll end the poll.
Oh, if you have 7, I'm not voting because I know the answer. Yeah.
Okay, I'm gonna end it now.
Mhm. You want to show the stats? Okay, we failed, guys. It's A. I know, it's so confusing because you're like, what? No way, it's A, right? But okay, so this is how SVM draws the line. Okay, it takes the innermost data point from the opposing classes and draws the line in between them. This line could be called decision boundary rather than line of best fit, because decision boundary is actually the more correct term rather than line of best fit. So the correct answer was the line that kind of like went diagonally like this, because it was touching the edges of these boundaries. Because if this data was not as clear cut as this data is, we would have a very hard time just dividing it in half like we did with this specific data. Okay, so this is kind of like the background knowledge on SVM. It's not too mathematical, but I think it's pretty clear. Okay, so let's do a practice. We're gonna do a game recommendation engine. See, this is what I told you. I really like classification. So the data, do I have the list ready for you? I may have the list ready for you, but actually for practice, I want you to try converting it on your own. So we have the output, which is the favorite game genre. I also classified these for you with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So whatever it's like, let's see, Fortnite, it's 1, right? So you want to say action. This is an issue with classification, and I won't go into the real coding solution for it in this session, probably next session, but you cannot feed words into a mathematical model, right? Like when I say this, it sounds obvious, but people obviously sometimes don't realize this. You cannot feed words into a mathematical model. Yeah. Oh no, new program. Everybody open a new REPL. If you try to use the same one, it would probably get really messy. So new REPL. Yeah. Did I also? Yeah, I didn't forget to give you the imports. I'll give it to you later. But yeah. Obviously, nested list format, and then your output should only be from this list. Yeah. And by the way, I'm not, don't quote me on this because I'm not 100% sure, but I'm pretty sure game rec engines use some sort of classification to do game recommendation for users. So again, classification, super, super, super useful. And by the way, if it wasn't clear what the graphics were like and the difficulty we're describing in price, is how much the user wants, like puts a value on these things. So for example, the user that has Fortnite as their favorite, right? I would say Fortnite has graphics level 8, difficulty level 7, and is medium cost in the game industry, right? So these are all applied to here. So when we do prediction, right, for user recommendation, it's going to be based on user preferences. Like how much does the user value graphics? How much does the user value difficulty or price? So, yeah. And again, don't forget to let me know in the chat when you got the input and output lists in the code. Okay, great. All right. So I'm gonna give you the import just so we don't get confused on anything. But other than that, I do want you to write the rest of these statements. You probably want to write them underneath your data and not above your data because we are referencing the names of the lists in the recommendation model fit. So again, like you can see over here, we're using fit in almost every circumstance. And I just called it recommendation model because it's more than just a model, but you can just call it model again. No big issue here. And then SVC is the support vector computation, I believe. So SVM is the support vector model, and then SVC is the actual linear algebra stuff we use to make the model. Again, we're not going too much into detail, but there are multiple ways to use classification, but this model is pretty accurate. So yeah. All right, awesome. Okay, so here is the data that you want to use to predict. Now I will remind you once again, because I didn't write it on here this time, when we predict, we have to do a nested list. I feel like that's my motto whenever I do AI. Don't forget the nested lists. So 5, 1, 16. So if I remember correctly, the order of the data. We want graphics level 5. We want multiplayer. I am 16 years old. Difficulty level that I want is 7. And then genre is 3. So FPS, first person shooter. And then what was the last one? Price. I don't want it to be super expensive. So 6 is decent. So I want you to tell me which which genre of game I should be buying. Oh, and actually, hold on one second. I'm pretty sure there is a little rounding trick over here that I don't remember off the top of my head when we do prediction. If it doesn't give you a whole number, let me know. I think we can do something about that. But it should give you a whole number, if I remember correctly. So yeah, rather than saying yes, tell me what your model got. So I know. Yeah. Okay. This time your model should be saying the same exact thing because we have the same data. So yeah.
What function do we input that data in?
This data you do to predict. So you do the whole what was it? Model.predict, and then you do the double the nested list, and then you put the data in. Yeah.
Okay, thank you.
Yeah, for sure. Again, that's the neat part about this. The predict and the fit and all that stuff is the exact same for all the models that we do. So pretty fun, I think. Yeah, here we go. Sorry. Okay. Looks like, okay. Looks like everybody's done. Okay, so next section, we're going to be applying our AI to actual game design. We're going to be creating the computer character, the MC. So this is a project that you will be improving probably next session as well. I'm still working on improving my own AI for this one. So it's a oh, what would you call it? A curve, a learning curve in this one too. So we're going to be creating a rock, paper, scissors AI. So how can we make an AI that beats us in rock, paper, scissors? Now, I believe on the internet right now, the record is 70 something percent. We will be bringing it to a solid, not this time, but next time, we can bring it to a solid 55 to 60% using the models that we will learn. I am working on doing a 70% one, so if you can help me figure that out later after you finish, yay. But for now, we will focus on this one. Okay, so go ahead and first, actually, you know what? Start a new REPL for this because this is going to be pretty big, and you'll want to like improve on it later on. So create a completely new REPL for it, like a project REPL. And go ahead and first code the basic rock, paper, scissors. I'm assuming I don't really need to explain this part. Like you can use numbers, user input, you want user input, and then the series of if-elif statements. You can code it however you want. I've had students do it completely with numbers, completely with words. But do keep in mind that we're not actually doing the MC just yet. So yeah. Or actually, yeah, why don't you also code a very just random based MC? So just like the computer generates a random number between 0 and 3, or between 1 and 3, and let's say 3 is rocks. You get what I mean. Generate random number, give random output. That should actually give you, should give the computer about a 33% win, which you're like, oh, typically people are like, oh yeah, it's 50%, right? But for some reason, stats 33% of the time only the computer wins using this model, just the basic random model. So increasing it to 50 to 60% is pretty considerable. Yeah. Let me know once you're done coding basic rock, paper, scissors in the chat. This should take like a solid 5 to 10 minutes. Yeah. And you don't have to play this 10 times if you don't want to. But if you want to see the point of the 33% illustrated, go ahead. By the way, I don't know if this is going to be useful for you or not, but do keep in mind that again, when you're creating AI models, you cannot feed it words. So you may want to consider giving each like word, like rock, paper, scissors, a corresponding number between 1 to 3. It will make your lives easier and less likely to have errors in your code. Oh wow, 20%. Did you run it like 10 times, Nick?
I ran it 10 times and chose rock every time.
Oh my god. Oh. Oh my god. Wait, it chose rock every time for 10 times?
No, I chose rock
Oh,
every
you chose
time,
rock every
and
time.
I won 7 times.
Wow. Yeah, I told you at this level, the computer is pretty trash, not gonna lie. 5 ties, 3 losses, 2 wins. Is that for the computer, 2 wins? Oh, for you. Okay. Yeah, ties do happen often, not gonna lie. Okay, 4 wins, 3 ties, 2 losses. Yeah. Yeah, but the computer should probably win only about 3 or 4 of the times, I think. Yes, 4 ties. Yeah, 3 or 4 sounds pretty reasonable. Yeah, and sometimes 2. When I've had students who try to run this algorithm like 40 times. Don't ask me why, but they would get like around like the 30 to 40% computer accuracy. So now after everybody finishes this, did everybody finish? 1, 2, looks like it. Okay, so now we're going to bump up computer win rate to like the 50 to 55, 60%. Okay, let's start. Wait, let me just make sure everybody got it, because otherwise it's gonna be hard to catch up. 1, 2, 3, 4, 5, 6, 7. Yes, okay, good. Okay, so creating rock, paper, scissors AI. Okay, so input this time will be patterns. Okay, so unlike linear polynomial regression, we cannot use any type of regular graph model, right, to predict what the user is going to put. But users do have patterns in which they use. Like, for example, when my sister was younger, she would start with rock every single time. But a computer wouldn't know that. But me as a smart person, right, I'm like, paper, paper, yeah? So same idea. So for example, let's say that the history of the user is 1, 1, 2, 3. In this scenario, let's just say that 1 is rock, 2 is paper, and 3 is scissors. Okay, it does not have to be like this for your model, right? This is just an example. So if we want to predict the third decision that the user makes, what would we take as the input? Now, notice that I'm saying the third decision that the user will make, meaning what would I have to take as my input? What do you guys think? What would be my input if I'm trying to predict the third decision? Anybody has any ideas? If I'm trying to predict the third decision, meaning what am I using as player history to back up that third decision? The first 2 decisions. Yeah, so I'm going to be using the first 2 user decisions in order to predict the third. Now, let me ask you, if the user just played 1, 1, what can I expect the next outcome to be? Anybody in the chat or out loud? I don't care. If the user just played 1, 1 and I'm predicting the next choice. Look at the list. If the user just played 1, 1, what can I expect the next one to be? Just from the history list that I have here on my screen.
1 again.
Why would it be 1?
I was thinking that it would be 1 again because if the computer sees that like every single time that it's been reporting a number that it's been 1.
Right. That would be a great other algorithm, by the way. That's like something we would add on top of it. But let's say that just using the list that we have over here, if that's all the data the computer had, and the user just played 1, 1, according to this list, it would be just the next number.
Oh, 2.
2, right? So if I was a computer and this is all the history that I had, right? I'm saying, oh, the user just played 1-1. So the next outcome they're going to play is going to be 2, right? So some people think that I would want the number to beat that, but actually you don't really need that. You just need a number that the user is going to play. And then in your function for the computer, you can decide what the computer needs to roll out. Okay, so here is our input list. I did every single possible combination of 2 in order that I had in this list. So 1-1, 1-2, 2-3, 3-1. That's all I did. So 1-1, 1-2, 2-3, 3-1. So that is the input list. And again, we're looking 2 steps back in order to be able to predict the next move. So go ahead and copy down this input list into your code. Put it in either a global place, or I don't know how you structure your code, but a place where you can access this throughout your entire code. And then let me know when you're done. And actually, while we're at this, it will be pretty advantageous for you guys to also copy down this list and store it as history. So like add another list on top of this. It will not go directly into our actual AI, but it's going to be extremely useful. So 1-1, 2-3. And then say yes in the chat when you're done. Okay, great. Let me trash this. Now let's talk output. So we already technically talked output, but you want to create the output list. So for 1-1, the output is 2. For 1-2, output is 3. For 2-3, output is going back all the way around to 1, and then 3-1, output is 1. Yeah. So you want to create that output list, correct place and everything. Yeah. Do I have it on the screen? I don't remember. No, I don't. And then just say yes in the chat when you got the output list. Okay, great. Moving on. Okay, model. So this is sort of a design question, but I think it should be pretty obvious. Which model do you think we will have to use? Linear regression, polynomial regression, or SVM, aka classification? Which model do you think we'll have to use? Feel free to either say in the chat or turn on your microphone. Anybody think they know? No. Yeah, it's a bit confusing when it starts to get in other contexts. Let me ask you this. Do you remember the description of classification? Like I would say the root of the word classification. If this was an English class, what would be the root of the word classification?
Classifier class.
Class, yeah. So when we changed everything to numbers, what does each number indicate?
A class.
Class. So, right, because rock, paper, scissors, these are not numerical predictions. These are classes that we're predicting. So the only answer that can work in the context of this game is classification. And that's kind of like the process that you always have to have when you think about AI, because as you learn more, I'm not necessarily saying I will teach you dozens of models, but when you continue, you will learn dozens of models, right? And you kind of have to have like this more of a design mindset in order to be able to apply them correctly. Okay, so go ahead and create your model and fit your data. So import correct classes and libraries. If we're doing SVM, it's just the same as we had before. So like it's in the chat. Hold on. It's in the chat somewhere. I can resend it. Okay, here we go. Copy. So that's the library that you want to import. So from sklearn, import SVM. And if you want the reference to how we made the model, it was over here. So we did model equal svm.svc, and then we fit our data. And again, you probably want to do this either in global context, if you did functions, or in a place where it's easily accessible to you, so outside of any for loop or anything like that. And then say yes in the chat when you got that part. Okay, nice. Okay. All right, so player function. So again, I don't know how you structured your code, but this is going to be a recommendation. You don't want to have like 100 lines of code with absolutely no functions, because that will make it a bit messy and difficult to reference later. So if you haven't yet, create a function for the player, call it getPlayer2. The reason it's called getPlayer2 is very simple, because this exercise was mainly focused on the MC. So it should have 0 parameters and only return the user's choice. So it's just like input statement, return user input. This one is not a necessity, but next time what I want to do is, you'll see, but we want to make your models compete against one another eventually. So it will be a lot easier to do if you have functions. And then just say yes in the chat when you're done with that. Okay, nice. All right. Okay, so MC player function. This one is going to be the big one. So create another function, call it getPlayer1. We will be using the last 2 choices the user made from our history list, okay? So create a new list to store those two and call them data set. Yes. Hold on, let me give you a bit clearer instructions because I just realized this is not the clearest. Where's my get player one? Okay, I can show you this on the board. So from your history list, yes, you have your input, but I don't actually recommend touching your input for this because when you're, especially since your model is based on your input, you want to keep your input pristine until you really need to change it, okay? So here's what I would recommend. You have the history list in your code. So what you want to do, if you want to do something that's going to be similar to this. So data set or data record, doesn't matter. And then current, so you're going to have to repredict the data from the data record. It will be the easiest if you do that. Because remember, when we predict, right, it's nested. So this is the part where I'm saying people are having issues with nested lists because it's not intuitive to do this sort of thing. You want to pull from the history, which is already represented in your input. But anyway, you want to pull from your history. You want to put it in an extra set of brackets. And then the 0 over here is to make sure that your answer is rounded. Because your algorithm is going to only respond, I'm guessing, to 1, 2, or 3, right? It's not going to respond to 1.5. So if SVM, for some reason, gives you a 1.5, you want to be able to round that. So the 0 at the end, like this, is to make sure that your answer is rounded. And you want to actually not return current quite yet, because whatever current is, you need the computer to give you the number that will beat the current, right? So for example, let's just say 1, 1, right? If the user just played 1, 1, and you get the current 2, you don't want to give 2, right? You want the computer to play, let's say we said rock, paper, scissors. So if this is paper, if 2 is paper, you want the computer to play scissors to beat that, right? So you need another series of if-else statements here, my guess. Again, depends on how you structured it. If you have like a separate function for if-else, do that. But yeah. And I think this will be all we have time for today. So we'll probably just finish this off next session. Yeah. And I have the reference up here. By the way, though, sadly, this is not at the 50% level just yet. There's like one additional step we will have to do to get it to the 50% level. And I think that's the coolest step, honestly, but we don't have time. So just finish up the MC one, and then we'll finish this off next week. And if you need any help, let me know before the end of class, so that next time we'll be able to jump right back into it and finish this off. All right, so it's 6 p.m. Yes. All right. Does anybody need this slide to stay up a little bit longer? I don't mind staying a couple more minutes. If not, then I guess we could end this session, and I will hopefully see you guys next week to finish this off and learn some new stuff. All right. Bye, everybody.
Thank you.
Thank you.
Thanks, everyone.
Yeah, thanks.